Today I, 人字草, and that's 词 as in Hertz, 草. And yes, I have a two-part first name. I will prove to you today that Einstein's relativity is a great mistake. That he is irrevocably, irreparably wrong. Now, before I begin, I must note that I only thought of very few more steps than Einstein did. But of course, we all know that sometimes great breakthroughs come from very small steps. Einstein did a good job. He took Maxwell's equations and he merged them with the mechanics that they knew of at the time. Okay, that's good. The problem with having something that's mathematically apparently sound is the not so minor fact that in theory and reality are the same. Reality kindly disagrees. You will be shown exactly how reality disagrees with him. Now, we must note that Einstein was a good scientist. He was brave. He dared to come out and speak and say that, oh yes, we must have relativity. Yeah, the principle of relativity is of course correct. It was later on that he made his mistakes. But the point is, he was very respectable. Of course, then, if there is a mistake, then correcting it must also be respectable. It has been 110 years since he created his special relativity and essentially paved the way for his so-called general relativity. In early 2015, I proved that Einstein's relativity must be wrong. So I sent my papers to a bunch of major journals and some famous physicists, and these were the titles that I used. This one has since been renamed to match this presentation, which is the great mistake, relativity. Now, in this one, I proved that relativity was wrong. In the second paper, Surpassing the Speed of Light, which I actually wrote earlier, I demonstrated exactly why modern accelerators, by design, even if the speed of light is not a speed limit, and we will show why it is not, cannot possibly accelerate a particle to over the speed of light. Now, naturally, nobody wanted to rock the boat because, well, a lot of them depended on this boat staying afloat to get paid. I am the first and to date only person who has managed to use science and math to prove that Einstein must be wrong. I expected, of course, to take quite a long time for relativity to leave the textbooks. Consider geocentrism. The first person to propose that, no, the sun does not go around the earth, it's the other way around. The first person to do this was a little bit after Democritus. You might be thinking, who is Democritus? He was a guy who proposed the atom, and he is a guy who essentially gave the atom its current name. So, Democritus was sometime around the 4th century BC. The first guy to propose heliocentrism was around the 3rd century BC. It was not until the 1700s CE, yes, that's the term these days, 1700 CE until heliocentrism was actually broadly hailed as fact. So this is how long? 2,000 years. Hopefully, it will not take 2,000 years for relativity to leave the history books, because at our current rate, I don't think humanity can last 2,000 years without discovering faster than light travel. So, there's always a disclaimer. Whenever you learn about this guy's relativity, there's always a disclaimer in the textbooks, and this disclaimer is valid. Relativity has never been proven wrong. Well, until my proof. But anyway, this disclaimer is perfectly valid. Why? For the simple reason that in science, you cannot really prove a theory right. You can only prove it to not be wrong at present. However, the fact that you haven't proved it wrong yet, well, up until my proof, does not mean it is right. Now, this photo should be very familiar to anybody who is a fan of Einstein. And this is from 1919, Arthur Eddington's expedition to around the equator, just south of Africa, just south of West Africa. And he took this photo of a solar eclipse. And they used this opportunity to look at the stars. Now, these stars, because the sun is deflecting their light, they look to be further out from the sun than they actually are. So when they calculated these deflections, Newton's mechanics would have given a deflection of 0.75 arc seconds. Now, 1 arc second, so you know that there's 360 degrees of arc in a circle, right? So 1 degree is 60 minutes. 1 minute is 60 seconds of arc. So Newton's calculations would have given a deflection that was 1 over 4,800 of a degree. Einstein's calculations was a little over twice of that. Now, even disregarding for now the question of whether or not glass in 1919 was actually good enough to produce this sort of resolution, even disregarding that, we will demonstrate in a later presentation why there is a problem with this. After 1919, Sir Arthur Eddington, who had been a long-time supporter of Einstein, he decided to go and give a talk. And after the talk, a professor at the university he was speaking at supposedly asked him a question of, Sir Eddington, what do you think of the claim that only 3 people really understand relativity? Eddington's response was pretty much what you would expect, given the fact that Einstein sounded like a Emperor's New Clothes scam. So the story of the Emperor's New Clothes, I hope you're reasonably familiar with it. But Einstein's claim was that, oh, it's fine if only a few scientists can understand me. What does a few scientists mean? He means, oh, it's fine if only the smartest scientists could understand me. Well, do you really think somebody's going to stand up and say, no, you are wrong? Well, quite a few people actually did. But most of people decided to wait and see if there was any proof that he didn't seem to be wrong at the time. So after Eddington's expedition, Eddington was actually proud enough to claim that, oh, only me and Einstein are special enough to understand his relativity. So everybody else decided to pile onto the bandwagon by claiming that, oh yes, relativity is correct, we always believed so. This probably sounds like elementary school bandwagoning to you, or cliques, but, well, these things happen. This bending of light would also have been predicted by Newtonian mechanics, but to a different magnitude. This diagram shows how a solar eclipse works. So clearly, when starlight is going around the sun, yeah, okay, it gets bent. We will demonstrate using this diagram in a later presentation why Newtonian calculations were not that far off compared to what they thought. So this guy is, you may and probably should have guessed that he is Sir Isaac Newton, given that we've been talking about Newtonian mechanics. And we've already seen that Einstein does not look like this. So, given the fact that this is an oil painting, even if we don't remember when Newton died, it's pretty easy to conclude that he must have died before Einstein's time. So he was no longer around to defend himself, or defend his theories, or modernize them even. Now, yes, Weberian electric theory was overtaken, but Maxwell was also just an approximation in the end. There are other factors that they don't seem to have contemplated that we will discuss in a later presentation. Einstein based his relativity on 2 postulates. The first one is not up for dispute. The principle of relativity states that every inertial frame is equally valid. This is not disputable. The second one is that the speed of light is constant when observed from any inertial frame, regardless of the speed of the frame or the speed of the emitter of the light. Or velocity. Fine. This is where his problem is. This will be proven to be very much wrong very, very soon. Why? Because logically, we will demonstrate that it simply does not match up with itself. Now, our first experiment is on the subject of deconstructing Einstein's simultaneity. Alright, so here, this is what simultaneity looks like in textbooks, or Einstein's idea of simultaneity. So his idea is that when O and O prime match up in position, two lightning bolts strike the ends of the car. So it makes two scorch marks. The person in the car sees the light from in front before the light from behind. They specifically say that, oh, this is not necessarily simultaneous. There is one problem with this. When the car is moving, there is one moment, and only one moment, in the car's frame where it observes that O and O prime are lined up. From the station's frame, or the track's frame, they also observe one and only one moment where O and O prime are lined up. What does this say? This says that those two moments must be the same moment, because there is only one moment where they line up. So, if at this moment these two lightning bolts strike the ends of the car, they must have done so simultaneously in both frames, because it's the same moment. Location correlates to time, and therefore one point in location correlates to one point in time in this case. Here, the funny thing about this is that it actually runs straight into Einstein's own second postulate, and he doesn't even realize it. So, he says that he runs into the signal from in front before the signal from behind catches him. Wait a second. All inertial frames are equally valid. Why are you telling us that your light is propagating in the frame of the tracks instead of propagating in the frame of the car? In the frame of the car, since there was one moment when these two lined up where the lights happened, then given that it's the same distance to the middle, and they occurred at the same moment, and they move at the same speed, c, relative to all frames, as he says, then they should meet at O prime at the same time as they meet at O. Now you might realize something. The wave front of the light clearly hits O before it hits O prime. Thus, we will demonstrate very simply, well, we pretty much have already demonstrated, that his second postulate must be wrong. But we will demonstrate it a little bit further. If you are not already laughing at this point, then consider the fact that Einstein's idea of simultaneity and of something happening or not versus his observations is essentially that, oh, it didn't happen, therefore, well, I mean, I didn't feel it happen, so therefore it didn't happen. I'm pretty sure we figured out that this is false when we were still playing peekaboo with our parents. So Einstein seems to have skipped this class for whatever reason. Perhaps he was too busy doing something else. So, let's approach this simultaneity problem from a middle school perspective, which, by the way, is exactly what Einstein did. So, this object, well, this observer, sets out from this point at speed 0.2 y. This observer sets out at speed y, and this observer sets out at speed y, velocity minus y. So what happens? Well, this observer will catch up 1/4 of the way over here. This makes sense. It travels 5/4, and this one travels 1/4, 1 to 5. And these two meet somewhere before this point. Yes. Does this sound like Einstein's simultaneity yet? Well, it does, and it should. So here are the calculations. You should feel free to scroll through them quickly, or we will scroll through them quickly, and you are free to pause at any time. Now, as we see, all these calculations are reasonable. So, the moving observer will end up seeing the same thing. When the light catches up to him, he will see the same as the stationary observer whose location exactly corresponds to him. Well, or when the other observer catches up to him. Let's not say that it's light for now. That would be university level, which we will do in a moment. The other observer catches him at a point where he ends up meeting the other observer at the same time that the person on the ground at his position meets the other observer. This makes sense. Now, both the observers coming from the ends meet in the middle. Yeah, that makes sense. So they arrive at the middle simultaneously. And they do not encounter the moving observer simultaneously. So, Einstein's simultaneity, which does not consider locations and how locations correspond to time, is meaningless. Now, if we are doing this at university level, all we have to do is set the speeds to some fraction of c. As we can see, clearly O3 and O2 will still meet at this middle. And O1 prime will say that, oh, they occurred at the same time. O1, if he is Einstein, he will insist that they didn't occur at the same time because he met the signal from in front first. Wait, whoa. What are you doing? You know that those two set out when O1 and O1 prime were lined up. That's one moment in time. So that you know that they set out when they were the same distance from you. Even with Einstein's idea of length contraction, that only depends on the relative speed of the frames, not the velocity. Which means that this would be contracted the same as this, and they would still be the same distance away. And therefore, the light should take the same time to reach him. But that is not what Einstein says. Einstein says, you see the light coming from in front first. If Einstein were to be riding a bicycle with a very long pole with two firecrackers at either end, and he has an electric trigger with the same length of wire, so the same time, for both firecrackers, and he presses the trigger, he would insist that the firecracker in front went off first, based on the sound reaching him first. This is not what his second postulate says. Now, for an animated demonstration, let's take a look at this. Alright, so for an animated demonstration, it looks something like this. So clearly they met here at the same time, and these two were discovered by O2 prime at the same time. Well, there's no basis for Einstein's simultaneity here, and this also destroys his own second postulate. So, we can extend this is the text of our problem. We will scroll through this fairly quickly. And these are the same observations we made earlier, essentially. So we won't spend too much time on it. The point was that in the end, if we strictly enforce Einstein's second postulate, his own simultaneity must be wrong. And there are also other implications that we will very soon discuss. So if his simultaneity, his perception of time, is wrong, and by the way, his simultaneity actually made up the basis of his relativity in terms of perception of time versus reality of time. So if his simultaneity, without counting for location first, is wrong, then we must conclude that time dilation, which his simultaneity leads to, will also end up being shown to be impossible. Alright. Here, we have a slightly longer track. We have a train, or some type of vehicle. So there is an observer inside. There are observers outside as well. How do we know that these two pulses are flashing at equal intervals in their own frame? Well, just look at the pulse fronts. So these two pulsars are giving off pulses of light, and they meet at the middle. So they are flashing in synchrony, simultaneously. So what about this observer on the vehicle? What does he see? Well, this is 0.5 c, half of light speed. So this distance here is equal to ct, t being the interval of flash. And how long will this vehicle take to get here? Well, it takes 2t, right? Because half the speed of light, whereas the pulses propagate at the speed of light. And remember that because position correlates to time, we can define the flashers as giving off one flash when he is here, giving off one flash when he is halfway between, giving off a flash here, giving off a flash here, here, and so on. So, this is the problem in text. Please pause if you wish to review the text. Now, after time 2t, we arrive at this point. Okay, do the pulses look reasonable? Every observer observes the reasonable pulses? Yes, they do. What about this observer inside? What does he observe? He must observe the same thing as observer D, or observer O1 does. So, at 4t, he observes the same thing as observer O2 does. Now, this is not what Einstein would have said. Why? Well, consider the following. Now the vehicle begins to move, or maybe we unpause the progression of the events. Who knows? Whoa, how long did this wave, A4, earlier take to catch up with him? It took 2t. Whoa. Einstein says that it should only take the contracted length here, divided by the speed of time, to catch up to him. So, we know that all the pulses we recorded are reasonable, according to the distances. Then what does this say about when we use Einstein's approach? We conclude that the time needed for one pulse to catch up to the car started on pulse A3. So for pulse A4 to catch up to the car, it took time 2t in the external frame. Fine. This is alright. What about in the car's frame? Well, we know that according to Einstein's length contraction, the distance must be some multiple of CD, or some multiple of CT, if you prefer to use this. CT instead of CD line. So, this says that the time it takes for that light to catch up must be nt. Why? Because it must be a length of nct, where n is Einstein's contraction. What n is irrelevant. We will not calculate it because it is not important for our problem. Now, the conclusion for internal versus external time. By the way, according to Einstein, the ratio of internal time to external time should only depend on the relative speed of the two frames. This means that no matter which direction you are moving in, it should come out to be the same. Or at least which direction you are moving in as far as the calculation is concerned. So, here, this ratio is what we get for internal time to external time. Alright, this is fine. This isn't a problem. This is a problem. What about the light coming from in front? The light that comes from in front must spend times 3 nt according to Einstein's speed of light postulate to catch up to the car, or to run into the car from the front. It takes time 2t from the external perspective. So the ratio of internal to external time must be 3n to 2. So essentially, Einstein is telling us that n over 2 is equal to 3n over 2. Therefore, Einstein's conclusion is 1 equals 3. So this is clearly not right. It is mathematically true that 1 minus 1 over infinity, which is 0.9 repeating, is technically equal to 1. It is, however, not true that you can say that 1 equals 3. Therefore, we must see that time dilation due to the speed of light must be self-contradictory. It just runs into itself, in a sense, and flops. So, more importantly, this means the speed of light cannot be restricted to being constant in all inertial frames of reference. So Einstein's second postulate has been shown to fail. So in our second experiment, we will resort to what is essentially an elementary school method of doing things, also known as Newtonian mechanics, or alternatively common sense. So Newtonian pursuit. Well, first let's count some pulses. So we saw earlier in our diagram that all the observers were seeing various pulses, and these pulses are reasonable according to their distances and the times. Now, Einstein's speed of light postulate, let's just say that for now we haven't proven him. Say we haven't proven him wrong. If we haven't, let's prove it in another way. Although we already showed it to be wrong. The speed of light postulate says the speed of light in vacuum has the same value c in all inertial frames. Alright, so let's prove it wrong again. These are some of the calculations we use. So we consider the distance between light pulses. This is each distance is what? Ct. C being the speed of light and t being the time interval, right? It is also equal to the length of CD in the diagram. So here, well, we list our calculations, and we consider how O prime might use the light pulses to measure his own displacement when knowing how long each light pulse is in the external frame. So he's trying to measure his own displacement in the external frame by applying knowledge that he has of the external frame and these signals that he is getting. So, we saw very clearly from the animation and from the diagrams that when the vehicle moves from C to D, or D to E, or E to B for that matter, it moves a length of Ct in the external frame. Sure. What about when he's measuring from inside? Well, he sees 3 light pulses pass from in front. He sees 1 light pulse pass from behind him. And he also sees that the light from behind him has undergone 1 positional shift relative to him. This is slightly different from having a pulse pass by you. What does this actually mean? Well, we know that the pulse length is constant, right? And we know that that's because the speed of light is constant in the external frame, and according to Einstein in all frames. And we also know that the time, that interval that they're flashing at, is the same. So, And this is like 2 steps forward and 1 step back. Except in this case, you're going 3 pulses forward and 2 pulses back. Or rather, 1 pulse back and you're sliding 1 pulse back, in a sense. So this matches the reality of a move from C to D. Why? Because your displacement ends up being 3CD minus CD minus CD equals CD. So, this observation by the person inside the vehicle observes that he must move this far. This is the same as observed from outside. So, if the object was not moving, it would be overtaken by an equal amount of waves from both sides. And they would calculate a positional shift of 0. 0 pulse gaps. And, well, 0 in general. What about the other people from outside? They also measure the vehicle as having a positional shift of 0. The result is that there is no need for length contraction here. It is irrelevant. And without a length contraction, do we even have relativity? No, we can't. And then let's think about Newtonian pursuits. Like, how does the light from in front, which is emitted at equal intervals as the light from behind, pass by him 3 times as fast? Why do we say it's at equal intervals? It's because if Einstein's length contraction is correct, and it's not, by the way, then this person, he notices that there's one moment when he passes point C, there's one moment when he passes midpoint CD, and there's one moment when he passes point D. And these are equal intervals, these 2 intervals here. Which means that if a light was emitted from both emitters when he was at point C, and one when he was at the midpoint, and one when he was at point D, well then, they're at equal intervals. Why then does the light pulse, does he encounter 3 wave fronts, so to speak, from in front, and only 1 from behind? Well then there must be a relative speed of light. In calculations, it looks like this. And we lead us to these conclusions. From this. This is not complicated. Of course, well, I mean, it's not complicated to any of us except Einstein, I guess. But the point is that since the light pulses from in front are at the same intervals as the light pulses from behind, and they're passing 3 times faster, then therefore they must be moving 3 times faster than the light pulses from behind. And what does this do to Einstein's second postulate? It blows it straight out of the water. This is once again a very similar issue to the 1 = 3 problem. I know not how Einstein's mind works, but apparently he believes that 1 = 3. This evaluation here is important in the sense that using the speeds of light, the relative speeds of light that the person in the vehicle found, he can find his own speed relative to the tracks. And once he has found his speed or velocity, the terms here are interchangeable for now, for the simple reason that all our velocities that we're using are in the positive, except for the light that's coming from in front of him. So, we know that the 2 light fronts are obviously closing the distance between them at 2c, relative to the frame that they're traveling on. Therefore, that's why we came up with the 3 to 1 must equal 1.5 to 0.5 thing. Do not think that relative to the other light, each light is only traveling at c. That is Einstein's mental shackle for you, and attempt to trip you up from discovering that his theory is clearly wrong. Now, this is the observer inside the vehicle calculating how long he himself takes to travel from C to D. He clearly finds that he must take time 2t. So there is no time dilation here. There is no length contraction, there is no time dilation, there is no relativity. Now, let's look back at figure 4. We see now that our belief that clearly Einstein is wrong is very reasonable when we actually look at the diagram and think for more than however long Einstein thought about this, which was probably not very long, given that we've figured it out. So this is some of the other math that came out to VO prime equals 0.5 c. We will scroll through this. So this observation from inside is equal to the speed observed from outside. Now, this says something very important for us. This says, of course, that if there is no time dilation and no length contraction, yes, distance over time is going to be equal to the other guy's measurement of distance over time, because neither distance nor time is stretched. Let's watch the animation again for fun. As we can see, the pulse emissions are at particular positions because position correlates to time, and therefore position can be used as a proxy for time. Whereas in Einstein's opinion, apparently this is not how reality works. Alright, so we have already expounded upon why this discovery of 2t is very important. Now, what do we actually see? We also see that under these Newtonian mechanics, we are not constantly trying to punch ourselves in the face and force ourselves into conclusions that are clearly wrong. So we see that Newtonian mechanics are at least consistent. Einsteinian mechanics do not seem to even manage to do this. So as a result, we must conclude that relativity is self-defeating and therefore not valid. And Newtonian mechanics seem to make more sense. So, well, perhaps we should consider taking another look at Newtonian mechanics and updating them suitably. For now, however, we've already proven that relativity is wrong twice. I have more proofs that are coming from different angles. Alright. So we've already proven twice that Einstein is wrong, and now we will do it a third time. Mutual time dilation. Now, of course, we must study how Einstein got the erroneous result of time dilation in the first place. His obsession with this, well, this is a very basic diagram. His obsession with time dilation began with his insistence that the speed of light must be c. In this diagram, this is kinematics. This is way before relativity in textbooks. So we clearly see that without a Vx, without a horizontal velocity, there is no parabola. Now Einstein's problem was his insistence that this beam of light move at speed c in the external frame. So there is something a little bit wrong with this. Think about what it means once he derives this equation, which is that the time inside, so say 1 second has passed inside. On the outside, it's many, many seconds. So say it's 3 seconds. Well, alright, so what does it mean when 1 second inside is equal to 3 seconds outside? First of all, he fails his own first postulate, which is a postulate of relativity, which is that all inertial frames are equal. Why? Because, well, we will very soon add another emitter, but we should note that for any postulate in science, there are two results. One is that it might be right, and the other one is that it is definitely wrong. For our first postulate, which is relativity, the postulate that all inertial frames are equal, there is no dispute. It must be right. Or as far as we know, it must be right. Therefore, we will demonstrate again that the constancy of speed of light must be wrong. So here we add another emitter, E. What does it do? Well, besides the tracks, we put two mirrors up. We shine this light up, and it comes back down. And the person outside is timing it, and gets the same time on his clock as the person inside for the light going straight up and down. This other light here that we add is progressing at speed c toward this mirror, and it is on a congruent path to light alpha inside. You might be wondering why I'm showing light alpha as having reached the end, whereas light beta has not even come close. We will show you why this is the case very soon. So this is a setup in words. And this is more setup. Yes, I know it is a little bit complicated, but think about the person inside looking out the window. Suppose that there are windows on this vehicle. Alright, so the light that's being shone up and down outside. So the person inside takes a look at it, and it seems to be moving backwards. So here are some of the vehicles that we might use for thought. And given that supposedly they are so good with measurements these days that they can measure 4 kilometers of track flexing by the width of 1 proton, which by the way was the gravity wave thing that they talked about. If you can measure that, then you can definitely use trains to measure relativity. Well, the width they found, the difference from the gravity wave passing, was supposedly 1/1000th of a proton's width. So, of course you can use trains for relativity. Now, what happens when the situation is stationary? So the lights go up and they come straight back down. And they are the same time. There's no dispute. Right? I mean, I hope you are not going to disagree with me that they go up and they come straight back down. This is the same distance, 2d over c, same time. Now, if we use this reference emitter added to the setup, and the person outside still sees the light inside is going diagonally, sure. What happens when the person inside decides to look outside? Well, let's look at what happens with the reference emitter first. The person inside will measure the same time the light takes to go up and down as the person outside will take for the reference emitter. Now you might be thinking, why is this and this reaching the bottom again at the same time? It's because Einstein's assertion that this blue light here must travel at c is very wrong. Why is this? Consider the moving observer looking out the window. So this reference emitter, she sees that her light is going straight up and down, but the reference emitter's light seems to be going backwards as she moves forward. So, each observer will see the other observer's light moving diagonally. These path lengths will be the same. Why? Because d, and this displacement horizontally must be the same. So therefore, by Pythagorean theorem, this must hold true. By the way, before anybody decides to say that, oh, Einstein decided to use Riemann geometry, not Euclidean, in his general relativity, we must remind you that he derived his basic equations from Euclidean geometry, using Pythagorean theorem. Now, what happens when the light goes back down? This path is exactly the counterpart. It is exactly congruent to the path that is taken from the other perspective. So the person outside sees this light is going like this. The person inside sees the light essentially going backward. I do realize that technically it should be over there, but for sake of space and to show that the lights travel along congruent paths, we show them overlapping like this. What does this say? Let us not forget that according to the first postulate, which must be right, that no frame is more valid than any other frame, then all frames are created equal, and no frames are more equal than others. So, if one of my seconds is worth 3 of your seconds, and one of your seconds is apparently worth 3 of mine, as is the case according to Einstein. Remember, this is only relative speed between the frames. So the person inside observes that the person outside measures 3 seconds for each second they measure. The person outside observes the person inside measures 3 seconds for every second they measure. So what is one of my seconds for me? It should be 1 of my seconds. So Einstein ends up giving us this. It's equal to 1 or negative 1. And if you still believe in Einstein at this point, that means you believe that either there is no time dilation, in which case Einstein is wrong, or that time flows exactly backward with respect to any other object. Why? Because this does not care about actual speeds. So mutual speed can be 0, and time would flow exactly backwards between any 2 given objects. The problem then is what happens when we add a third object. And the universe has, hopefully your mental model of the universe has more than one object in it. So that means Einstein is still wrong. Which means that clearly mutual time dilation destroys Einstein's entire theory. Now let's consider this from a slightly different perspective. Mathematically speaking, the time that must be measured for the light to return to emitter level from within each frame themselves must be this, 2d over c. Since we've already destroyed time dilation, there is no time dilation here. Therefore, the light that's going diagonally according to the outside observer, but is actually going straight up and down according to the one inside the vehicle, that light must end up reaching the bottom at the same time as the reference light outside reaches the bottom. So the time ends up all equaling 2d over c. And then, what happens then? Well, they can't observe time dilation, fine. So what happens when we add this beta light? The one that we saw earlier was still over here when the blue light had already reached the end, and when the red light has already come back to the bottom. We know, we are absolutely certain that light beta must propagate at c. So if light beta is propagating at c in the external frame, or with respect to the external frame, and we see clearly that it reaches the bottom after this light comes back, and this light comes back at the same time as this light comes back, what does that say? That says very clearly, according to all this math, that the speed must be greater. Well, here the time for that light must be greater than the time for the other 2 lights. And therefore, what does it say for the speed of the blue light relative to the external frame? Well, here's some of the math. So the speed here must be this. We see very clearly that the blue light must have been traveling faster than the speed of the green light, which was c. So, by the fact that mutual time dilation is impossible, we have again disproven Einstein's speed of light postulate. Because in the end, no frame is more equal than any other frame. And the animation that results looks like this. We see very clearly that by the time this finishes, the green light has not finished. These are congruent paths. Therefore, if the green light is moving at speed c and the blue light is faster, it must be faster than c. This is not up for dispute. Now, this is a slightly longer wording of the same problem. Alright, we have managed to disprove Einstein's relativity 3 times by 3 separate methods. Now let's take a look at how reality could work. So, Newtonian physics, at the very least, it does not contradict itself. Not as badly as Einstein's does. We've already proven that Einstein clearly just face plants so often. We will show a thought experiment that uses mostly Newtonian mechanics. And we will demonstrate why it is still reasonable, whereas Einstein is, well, not so reasonable. There are many more recent discoveries after Einstein's time. For example, black holes. The Schwarzschild radius can be calculated very easily by Newtonian mechanics, and it's still fully correct. So this says something, doesn't it? The problem was, after 1919, nobody wanted to be an idiot, or look like an idiot, by trying to go against Einstein. Now, in the common sense of science, to make an object move sideways, you must give it a horizontal velocity. And this horizontal velocity should not affect the vertical velocity. The only reason in many problems that students are forced to do on relativity that they must change the vertical velocity is because of this insistence that, oh, Einstein must be right. Yes, of course, if you start off with the assumption that Einstein is right, you will get the conclusion that Einstein must be right. This is not very complicated, is it, this reasoning? Well, it's not. The point is that we already observed several times from earlier that the speed of light pulse alpha must be equal to this. And by the common sense of science, it should be equal to this. And this is greater than the speed of light. So let's circle this, because it's important. Now, let's not use the mental shackle of Einstein's second postulate, because we've proven it to be wrong. And we see that, oh yes, we get a reasonable answer. Now, these are some of the calculations that we use under Newtonian mechanics, which are reasonable. None of these violate themselves. It is internally perfectly consistent. Under the common sense of science, these times should be the same. And as we saw earlier, reality should look like this. This is c. This is clearly c. But it's slower than that. So that is clearly faster than c. We should point out that experimental reality combined with good old-fashioned common sense, which by the way is a very bad misnomer because it is so rare. So reality is greater than relativity. It always has been, it always will be. The point is that Einstein's postulates, the first postulate is fine. The second postulate is strictly unnecessary, and it conflicts with itself in so many different ways that it is completely baseless. The unfortunate thing, though, is that for 110 years, nobody has actually managed to disprove it. Now, yes, Einstein based his second postulate on some reasonable experiments. The problem was that he didn't actually stop to think for a moment what happens when he applies the theory to reality. We will discuss some of the problems in a later presentation. Now, hopefully, I believe, at least, that all professional scientists who have watched this video will find it reasonable and find relativity to be less than reasonable. Now, it takes a lot of courage to stand up and shout that the emperor is naked, but we have done it. And hopefully you too will agree with us and shout that, no, Einstein must be wrong. And thus, physics will one day again have a real-time reference. Now, conclusion. Even other than the conclusions that we will draw, which will show that relativity has a ton of other logical holes. In point form, our thought experiments have demonstrated that Einstein's relativity is completely wrong. So, if it is completely wrong, clearly we must change to a slightly different form of physics. Newtonian mechanics, at least, is consistent. This is important. Einstein's are not. So relativity must be wrong. Now, I'm not saying that Newtonian mechanics must be right. Because just because something is internally consistent doesn't mean that it is necessarily right. For example, you can assemble a model that places Earth at the center of the universe, and it would be fine according to relativity, or the principle of relativity, in that no frame is more valid than any other frame. However, that doesn't mean it's right. However, at least it wouldn't conflict with itself as Copernicus' initial theory did. Why? You might think, hey wait, isn't Copernicus the guy who proposed heliocentrism? Or in the modern era? Yeah, the problem was that he insisted on perfectly circular orbits, which Kepler later showed to be false. Now, my experiments demonstrate that the 110-year-old speed limit of the speed of light is not in fact a speed limit. Alright, so there are some other conclusions that we drew. First, there should be one time base in the universe, a universal time that has been counting since long before Earth existed and will continue to count long after Earth is gone. Now, if a person says that their perception can dictate time, how time passes in the universe, that person is probably, well, has some ego issues, or thinks themselves really important. Under our above proofs, we conclude that Einstein's relativity is wrong. Alright, so the momentum of any object should resemble this equation. This includes speeds greater than or equal to the speed of light. And the kinetic energy should look something like this. It also includes speeds greater than or equal to the speed of light. The total energy should look something like this. Yes, Einstein's E equals mc squared is still reasonable. This again includes speeds greater than or equal to the speed of light, because we have shown the speed of light is not a speed limit. Now, in addition to the speed of light in vacuum not being a speed limit, a limited speed of light is also unreasonable. Without this shackling, we can get an internally consistent worldview. Whereas Einstein's worldview, sure, it might look pretty on the surface, and it might be like, oh, we don't need to try any harder. We can just give up on surpassing the speed of light. Sure. But then when you look closer, it's internally inconsistent. It already trips itself up. It seems that Einstein installed a big red self-destruct button somewhere in his theory. Now, it'll of course be a great story in the future about Einstein and his respectable theories. Why? Because at least he had the guts to go out and propose them. We should point out that in Einstein's time, it was a time of great discoveries. 1900 to 1905, that was a time where physics, well, many physicists were starting to get a little bit complacent. So they felt like, oh, we know everything that it's worth knowing. Einstein shook them up. This was good. Another issue with that time period was that they essentially would allow anybody to publish anything that was mathematically reasonable. Einstein's theories were mathematically reasonable, given his postulates. And his second postulate about the speed of light was based on several people's experiments to try to find the speed of light and whether or not the Earth's motion affected the speed of light. So they ended up concluding that light did not require a medium. It was a wave that didn't have a medium. Now, Planck was awarded the Nobel Prize after Einstein published his papers, but Planck was still very famous. So this was a time when the wave-particle duality of light really was being an issue. So essentially it was a tumultuous time in physics, and anybody with something that was mathematically reasonable could hope to get it published. This is not like the modern day. In the modern day, you need to publish something that seems reasonable to the majority of scientists. And if they don't agree with you, they will stop you. So Einstein was lucky. He didn't need to resort to basically shouting from a soapbox, which we are doing right now. However, we should note that we have yet to achieve speeds over the speed of light. Now you might be thinking, hey wait, if the speed of light is not a speed limit, why is this the case? If Einstein is wrong, why have we not seen speeds over the speed of light yet? In my other paper, or document rather, I have described exactly why modern accelerators, by design, cannot hope to surpass the speed of light in their own frame. Now, in this article, I also outlined an accelerator design that can surpass the speed of light, provided it is not a speed limit. Given the fact that we have already observed Cherenkov radiation, which is from particles that are moving faster than the speed of light in their particular medium, well, we should be probably observing something reasonably similar when it comes to actually observing things that are over the speed of light. We should be able to observe them from beside their trajectory and in front. In front in the sense that they run into you. Now, this should seem obvious when given that relativity is incorrect. However, it seems that many scientists seem to have forgotten that, well, time doesn't wait. If relativity is incorrect, then of course there must be one time base in the universe. And what else must be true? It also means that the faster than light age should soon be upon us. And we said this is if relativity is incorrect. Well, we have proven it is. Therefore, hopefully, scientists will come to agree with me and save humanity by bringing us into a faster than light age. As stated previously, we should note that to make mistakes in science is very normal, and it is of course very respectable. Why? Because at least you had the guts to go out and say something. Well, of course, if there is a mistake, then correcting it is also respectable. Let's make some, these are end notes that should really be noted about Einstein's whole theory. He essentially claimed that only the smartest scientists could understand him. This is the same trick as the emperor's new clothes. Now, he is actually right in saying that only a very few scientists could truly understand his theory. Why? Because this is saying that only very smart scientists can really understand him. And the thing is, any really smart scientist who, well, anyone who understands his theory at its very basis and does not immediately go, dude, this is wrong, is clearly not one of these few smart scientists. Emphasis on the smart. So, before watching this video, to believe in relativity is understandable. It is natural. Why? Because you are taught relativity. You have been taught relativity for the past 100 years. Well, I mean, people have been taught relativity for the past 100 years. So it is reasonable to believe in relativity before you watch this video. After you watch this video, if you continue to believe in relativity, well, it's your choice. But hopefully real scientists will no longer believe in relativity, at least as per taught by their predecessors. You should still believe in the principle of relativity though. Why? because that first postulate is not up for dispute. Every inertial frame is equally valid. No frame is more valid than others. Now, of course, we should note that real scientists, even after watching this video, will probably still have to teach their students relativity for the simple reason that curricula do not change that fast. So, while you're teaching your students this, make sure that you also enlighten them to the fact that relativity is wrong, and of course reference them to this video. As we know, it takes somebody very brave to stand up and shout, "The Emperor is naked!" And of course, it takes somebody very brave to stand up and claim that relativity is wrong. I am the only one in 110 years to finally have proven that relativity is wrong. So thank you all for watching. And of course, thanks to Mr. Einstein for managing to give me the chance to prove that he is wrong, to correct his 110-year-old mistake. And thank you to all these references, and these as well. And our final claims that we must make today, that I must make today, are that 2015 should be noted as the year when Einsteinian relativity was finally overthrown. And 2016 should be the beginning of the faster than light age. If you are watching on YouTube, please look lower on the page to the description section of the video, and there you will find links to my two files, namely The Great Mistake Relativity, originally titled Reconsidering Relativity, and Surpassing the Speed of Light. There will be more videos to follow, outlining other glaring mistakes I found with relativity and why I deem it worthy of the name Great Mistake. This video is brought to you by me, Renzi Cao, and this video also exemplifies how, and I believe the generation of physicists who are currently watching should know this reference. This is a case of the mountain crumbling because the pebbles dared to present themselves as tripping stones. Thank you for watching, and we'll see you next time.